Hey, good evening, Physics 143 students. We are still in chapter 23, and it's going to take us quite some time to kind of get through this. So I think last lecture we looked at light hitting a boundary of a transparent material. It is possible that light, when it encounters this boundary, may go straight through, and it will do that if the incident material, the material where the light starts, has the same index of refraction as the new material. If they share the same indices, and you take a look at something like Snell's law, then if the ends are identical, then the thetas would be identical, and essentially light will go in a straight line. Or if you come in on the normal line, and remember, all angles are measured with respect to the normal line when it comes to Snell's law. And if you do that, the sine of 90 is right one of these magic numbers, and that happens to be excuse me, not sine of 90, but sine of 0 is 0. And so if you come in on the normal line, which is at 90 degrees to the surface of the material, but all angles are measured with respect to the normal line, that's really sine of 0, and sine of 0 is 0. So you'd have to have 0 on both sides, and so the indices are never 0. And so those are really the only two ways that light is going to go through a new material and not have some sort of deviation from its current path. And the deviations are typically pretty subtle. They're not huge. And so, once you have a handle on, that light changes its direction when it encounters a transparent material under most circumstances, then what you do is start using the correct material and giving it the correct shape such that you can direct the light the way that you want to. And typically that would be, the function of a lens. So I'm looking down here, what is a lens? A lens is made of a transparent material that remaps the incoming light by using the correct material. The correct material means it has the correct index of refraction and the correct shape. So you've got to adjust for the shape to get the light to take the path that you would like, and also the correct material. Then the light bouncing off of an object hits this material and gets redirected, and we will redirect it in ways that are suitable for whatever the situation really kind of calls for here. Okay, so that's what a lens is. And so today's lecture is really based on lenses, and we're going to take this in two parts. So this will be, the first part. This first lecture, we'll be looking at light rays bouncing off of a material and then going through the lens, and then us being able to analyze what that light's doing and give it some names of exactly what it's doing. Okay. And then, it's a little bit cumbersome what we'll be doing today, but it does work. And then what we'll try to do is refine it and see if we can't use what we're doing today to find some mathematics that then gives us maybe a little bit more precision in the future of what light's going to do when it encounters different materials of different shapes. And then we'll eventually probably call that something like a thin lens equation. And so that will be probably the second lecture on lenses. So I think we'll be looking at lenses here, really kind of in two parts here. Okay, so lenses have something called a focal point. This would be a definition that you really want to have at your fingertips. But a focal point is the place that all rays that come in that are parallel to something called the optic axis will get sent. Okay, so light that is parallel, what that really means is that the object is far away. So if you give this some thought, it kind of makes sense. So if you have a maybe like a large redwood tree, right? So we see these things in town here. And maybe if you're just a few feet from the redwood tree and you look up to the top, then you look down at the bottom, and those light rays are coming to your eyes from very different angles, right? To be able to see this entire object. Now, if you keep the tree exactly where it is, and you back away from it, say several blocks, and this tree is going over people's houses, and you can still see it. Now the light coming from the top and coming from the bottom are coming to your eyes, and they're much closer to being like parallel. Now if you pick up that tree and move it several miles away, now the rays will be essentially parallel from the top and the bottom of the tree. And the further away you place the tree, really the closer and closer they get to being parallel. So objects that are quote unquote far away will have light rays that are parallel coming from the object. So even though the object may have size, the light rays are essentially coming in with all the same orientation relative to something that we're going to call an optic axis. We'll take a look at that here in a minute. And so the focal point is where those parallel rays converge. And then if I know where that point is they converge and I measure that to the lens, that will be called the focal distance. So most lenses will be categorized many times by a focal distance. Okay, and the focal distance is just a measurement from the lens to that point where parallel rays get sent. Okay, so somewhere like in a laboratory, it's pretty easy to grab some sort of lens and make this measurement. and I'll show you how to do that here, probably one of our lab activities. Okay, but it's important for us to know, one, what is a lens, and two, that they have this thing called a focal point, and that's where the parallel rays will converge. And I'll show you what that means here, really kind of in a moment here. Okay, but important definitions for us to be able to move forward, with having some sort of specific vocabulary that's going to be needed. Types of lenses. Let me change that here. Two types of lenses, and for the most part, they are positive and negative. And there are different names for positive lenses and for negative lenses. A positive lens, many times, especially by your textbook, will also be called a converging lens. Okay. And a negative lens, many times, especially by your textbook, will be called a diverging lens. And so we have to really kind of know what these words mean. So, if you're reading some sort of description where people, someone's saying, I have a positive lens, it'd be the same as saying, I have a converging lens. Okay, now typically, kind of the classic shape of a converging lens would be something like this. Okay, kind of fat in the middle, and when I kind of feel my glasses here, I kind of feel that they kind of do something like that. So I must have a converging lens, and then in a chapter or so we'll see who needs a converging lens and who needs a diverging lens. So typically people will need one or the other if they need some sort of correction to their eyesight. And this thing called the optic axis that I've been mentioning is really a line that kind of goes right through the middle of the lens, just sort of like that. And people refer to that as the optic axis. Okay. And now if I've got light rays that are coming in from something pretty far away, they come in parallel to each other. Okay. Now, when they hit the lens material, really two things happen. They hit this first boundary, right? They hit this first side right here, and they refract. That is, they change their direction depending on what the index of that material is and what the angle is they hit. So essentially, what you do is use Snell's law, and you redirect that ray. Okay. Then it goes through the material and hits the back side, the second surface, this one back here, and then it gets redirected again. Okay, and so Snell's law is alive and well here, but we're going to just kind of act like it doesn't exist, because what people have done is found kind of rules of thumb where you don't have to do the calculations, but the calculations would tell us exactly the same thing. Okay, so don't think somehow Snell's law doesn't work or something like that. It does. And so the lenses that we are looking at are thin lenses. And so, even though there is a refraction at the front face and the back face, the overall effect is that the light comes in a certain way and it leaves a certain way. And what happens in the middle of the material is really kind of inconsequential to us. Okay, and so these rays here, really do kind of hit, this backside, and they get redirected. And the spot where they all get sent, that is typically called F, and that is the focal point. That is the point where the parallel rays from an object that is far away get sent. And then this distance right here from the lens to the focal point, that's called the focal distance. And so if you have, quote unquote, a strong lens, that's one that's going to have a lot of curvature to it. It's going to have a very short focal length. And that means it's getting these parallel rays and really squeezing them together very quickly. If you have a weaker lens, so you'll hear, maybe sometimes the eye doctors and the opticians talk about this, a weak lens has usually very little curvature, and the parallel rays will come in, and then they focus. That is, they come together at some point that's far from the lens. And, some people will need something like that at times. Okay, so that's what a focal point is. And then these rays just kind of, continue on, in straight lines. So light takes the path of least time, which means it goes in a straight line if it doesn't change material, right? From point A to point B, the shortest time to go between those 2 points, if this is all the same material, is a straight line. So light is always going in a straight line until it hits a new material. Then the wave gets absorbed, re-emitted, absorbed, re-emitted, and that takes a very small amount of time, but it does take some time. So the wave kind of has some impediment to going through that material, and the effect is that it slows down going through the material, and that means it has to change direction to go from point A now to point B in the least amount of time. So all those things that we looked at last time are still alive and well, but people have found very, very nice, like I said, rules of thumb, where you just kind of don't have to do the calculation here. So, if I knew something about the curvature of the lens, that is the radius of the one face and the radius of the other face, and I knew what kind of material that was, I could do Snell's law on both faces, and I would end up with a ray that goes right through that focal point. So instead of doing the math twice, we just kind of have this little quick rule of thumb here. Okay, so that's kind of what's going on here. So now a negative lens, also called a diverging lens, the classic shape, and there's many different shapes here for both converging and diverging lenses, and you can take a look in your textbook, and he's got a number of very nice images there. But kind of the classic shape is, one of these shapes where it kind of gets skinnier in the middle. So it's kind of like, the inverse of the converging lens, where it gets kind of fatter in the middle. This one gets, kind of skinnier in the middle. And if I were to draw an optic axis, it would look like this. And let's see here, for some reason I erased this far side here. Okay, so if I get some light rays coming in here, and the light rays are coming in parallel to each other, once again, they hit that front face and they refract, unless the two indices of where the light is. Typically, you know, if we're talking about eyeglasses, it's in air, hits like a piece of plastic or a piece of glass that has an index close to 1.5, 1.6, 1.7, something like that. It gets refracted at that front face, redirects a little bit, hits the back face, and then gets redirected again. So once again, there are two calculations with Snell's law, or we just kind of learn these rules of thumb here. And you know, what ends up happening is that out that back face is that the light will diverge somehow like that. Okay, that is, they get further and further away from each other. And so, you know, it's kind of interesting here that, you know, if you strictly look at the definition of a focal point, you know, that a diverging lens looks to have, you know, no focal point at all. And that's actually not the case. And, you know, this will make more sense, you know, once we start playing around with the lenses and some of the vocabulary and, you know, what's really happening with the light here. But if your eye, you know, is over here, so there's your eyeball, there's some eyelashes and so forth, and these light rays are hitting and they're getting further apart, your brain plays a little bit of a game on with what's happening here, because in all of your experience with this world, light has always come to your eyes in a straight line. Okay, so your brain is always interpreting light coming to you in a straight line. And so when these rays are getting further away from each other, your brain says, well, they're coming though from a straight line, right? So it sort of acts like the piece of glass, the lens, is not even there. And your brain says, oh, they really came from some point on the other side of the lens, and they're all just going in a straight line. And so in other words, you know, if I were to, you know, get this line right here. So if your eye sees this light ray right there, it thinks it came, you know, in a straight line. And so I would backtrack it. And once again, you know, if I were to see this one down here at the bottom, then I'm kind of outlining in black, your brain says it came from a straight line path. And so it comes back here and you start finding this point where these light rays look like they have come from. So your eye is telling you, yeah, you know, they're really coming, you know, in this straight line path. And so that would be the focal point of this lens. And now notice it's kind of on the other side of the lens. As the converging lens gets light and actually converges it down to this focal point, and it becomes a focal distance. And your book calls that a positive lens. And so this distance right here is a positive distance. Okay. And so in other words, if the light keeps going that way, we're going to give it a positive sign. If we have to backtrack the light because our brain is telling it came in a straight line, then this distance right here from the lens to that point will be a negative distance. And that's why we have this name, a negative and a positive lens. The negative lens, the diverging lens, has a negative focal point. You have to backtrack rays and say, well, they look like they're coming from here to our brain. And that's what's happening here, okay? And so, you know, this is what a diverging lens does, and this is what a converging lens does. And so one thing gets something called a positive focal distance, the other one has a negative focal distance. And so, you know, if your eye does not focus light fast enough, and then you're going to need a converging lens. You need a lens to start converging it because your eye can't do enough of that, such that you can get a clear image on the back of your eye on the retina. If your eye focuses light too fast, that is, maybe your eye is too long and the screen is not getting the clear image, then what you need is a diverging lens. And so what you do is you have objects that are far away, it hits the lens, you spread the light out, now it hits the eye, and now the eye will redirect it with its own lens system into the correct on the correct screen, which is the back of your eye. Essentially, that's the movie screen that your brain is interpreting this light information and exciting these rods and cones in the back of the eye and so forth. Okay, so lenses have a focal point. It doesn't matter if they're a positive or converging lens or a negative or diverging lens. The diverging lens has a negative focal length, and the converging lens has a positive focal length. So they both have focal points. Okay, so eventually, when we're doing something like mathematics, that will be important. So one of them, we will tell the equation, okay, you have a converging lens, and the equation will know it's a converging lens because you will put it in a positive number for its focal distance. And then the equation will know that you have a diverging lens when you put in a negative number. And it'll just, work out the exact results of what the light's going to be doing, in either case. So it'll be, very, very nice. Okay, now let's take a little bit of a look here at light and what light is doing here, right? So light travels in a straight line. We know that it takes the path of least time. And so if you don't change materials, it's going in a straight line. And most of the time, that's exactly what it's doing. If you're not wearing glasses, if we removed a little bit of our technology, one of the few times that you would see light maybe not going in a straight line is if, you're looking and there's maybe a fish underwater and there's light coming off the fish. It hits the water air boundary and comes to your eye, and you're hungry, and you throw a spear at that fish, and suddenly your spear misses the fish by a fair margin because the fish actually isn't where your brain thinks it is, because the light got bent at that surface, right? And so just like you've seen a straw, that might be in liquid, and out here's air, the straw at that surface looks like it's disjoint. It looks like my finger, that disjoint there. And so a straw, we know is a sort of a straight continuous piece, but on some sort of clear liquid, it has a shape like that. And so at that boundary, the light is being redirected. And so, otherwise, your brain is always accustomed to thinking light's coming in a straight line, because in probably 99% of your existence, that's what's always taking place here. Okay, so light travels in a straight line until it encounters a new index n. And so, since it travels in straight lines, we will use ray diagrams to map what the light is doing. Okay, so a ray is just a straight line that shows us the path that the light is going. Now, remember, light is a wave, right? So it's really some sort of wave. And probably in a few lectures, when I look more at wave properties, I'll be able to probably use something like Huygens principle and show that this wave property can be approximated very nicely by straight lines. And straight lines just make very, very beautiful geometries. And so we don't have to really kind of worry about this kind of up and down nature of the electromagnetic wave or anything like that at all. Light travels in straight lines, so we're going to use straight lines to describe it. It's really kind of that simple. Okay, so when light hits a new material, the typical thing that we will do is have an object, and the object can be anything. Okay. So the object doesn't have to be very complicated. It could be like your pencil here. And you pick a spot on the object, and really light is bouncing off of every single part of this thing. And some of it comes to your eye, and some of it doesn't. Some of it bounces in other directions, and your eye never receives that light. But you pick a single spot on here, and the typical thing that people do is pick the top of the object and say, okay, I've got some light coming off the top of the object. And what is it going to do when the light bounces off, right? It's going to come off in all directions, but some of that may hit your lens. And when it hits the lens, depending on the angle that it's hitting at, it's going to do something a little bit different. And so that's what we end up doing. We look at an object, we pick just one spot and see what does light from that one spot do. And once you kind of pick that one spot, you really kind of know what it's going to do from all of the spots. So you don't have to, pick this spot and that spot and that spot and that spot and that spot. We just pick one spot and say, okay, what's the light doing from there? And then we just use our common sense to see exactly what, is going to take place with the rest of the object and how the light from that's going to get remapped or redirected from our piece of clear plastic or glass that we happen to put in the way. Okay, so the rays that we will draw, these are 3 rays, and you really kind of want to know these 3 rays. They're not very complicated, but we need 3 rays. Most of the time, 2 will give you the result that you need, but there are many instances where you cannot draw all 3 of these rays. So 2 is needed to get a result, but sometimes one of these is going to be eliminated from the geometry of the situation. So I'll show you what that is here in just a second. Okay. So number 1, any ray parallel to the optic axis will pass through the focal point. That makes sense. I just kind of scribble that up above, but that's the definition of a focal point. That light that comes in parallel to the optic axis, which is just this imaginary line that kind of really goes right through the middle of the lens. If you come in parallel to that, then that light will all be sent to the focal point. Okay, so when we have light bouncing off of my object, well, one ray may come in, if I have a, some sort of, lens over here. So if my red eraser is a lens, and light bounces off of the top of this object, and it comes off nice and straight and parallel, and it hits this material. When it hits this material, it's going to get redirected right to the focal point. Okay, and so that's what the focal point is. And so this is just a ray that really is just describing the definition of the focal point, but it's one that's going to benefit us, in the long run, just time and time again. So this is really kind of one that you can't always draw it, but when you can, you will. And so it's very, very helpful. Okay, ray number 2. Any ray passing through the focal point of a lens will travel parallel to the optic axis once it passes through the lens. And so this is kind of the inverse of the first ray. Okay, so let me kind of just give you a little bit of a sketch of what's taking place with both of these. So it kind of makes sense. So the words are describing something that, becomes kind of meaningful here to you. And so, this first one, we've already seen, but, let's just say that we've got a nice lens like this. Okay, it's just a kind of a typical looking converging lens. And its focal point, say, is out here. And if you have a light ray that is coming from an object, so here's the object. And so the object is like my pencil or something like that. And so if some light comes off the top of the pencil and it hits the lens, now there's a lot of light that doesn't hit the lens, and I don't care because it's, the lens doesn't care, it didn't hit it, so it's not going to, redirect those rays. But if some light comes off the top of this and the light comes in parallel to the optic axis, it gets sent right through that focal point. And so the deviation of the light is very, very modest, right? It's very subtle. It's not, at least on this focal point here, it's not a strong lens where it comes in and really gets redirected, where you'd have a lot of curvature on the lens or something like that. Okay, so that is ray number 1 right there. A ray parallel to the optic axis will pass through the focal point. Okay, and that's what I just sort of drew right there. Okay, now ray number 2, that is very useful for us to see what's happening to the light. Instead of doing a bunch of calculations, we can just draw these lines pretty fast. And a lot of times, I don't, being a physicist, I had to prepare for, national exams that you have to take and pass in graduate school and things like that. And a lot of times, they have these things set up where they want you to do a bunch of calculations. And if you just kind of just really quickly do a little ray diagram thing, you have the answer just within seconds, right? So there's just no calculations really sort of necessary. So these things are very, very useful. Now, it says a ray passing through the focal point of a lens will travel parallel to the optic axis once it passes through the lens. Okay, so on a converging lens, what you find out is that if this is the focal distance, you come on the other side of the lens, the same distance. Well, if light is coming this way, it will, if it comes in parallel, we'll go through that focal point just like that, right? If it comes in parallel this way, it's going to go through that focal point. So in other words, a converging lens will have a focal point, and it's really on both sides of the lens. And so at times, let's get rid of this here just to clean this picture up here. So at times, what you might have here is an object that might be kind of far from the lens, okay? And so, let's put it, maybe out here. There's my object. And so let's get this optic axis and kind of extend it out here. Now, if I have a light ray that comes from the top of that object, and it does what number 2 is describing, it passes through the focal point. So a ray that comes off the top of this thing and goes through the focal point and then hits the lens will be sent parallel to the optic axis. So it's going to look just like that. That's ray number 2. So it went through the focal point and it comes out parallel to the optic axis once it passes through. Okay, so parallel in, through the focal point, through the focal point, parallel out. Essentially kind of almost like inverse operations or something like that here. Now you can see that ray number 2 cannot be drawn all the time, right? If your object is inside of the focal point, you cannot have light go from the top, go through the focal point, and then hit the lens too, right? Because the lens is on the other side of the object. So in that case, you cannot draw ray number 2, which is why we really need a third ray, because you always need 2 to really kind of give you the results that we really want. Okay, and this one might make sense here too. It says any ray that passes through the center of a lens perpendicular to the face of the lens will pass through the lens undeviated. And my computer is saying that I made that word up, undeviated, and that's okay. But undeviated means it goes in a straight line. It does not deviate from its course. So no matter what Microsoft Word says. Okay, why is that true? That is true because of Snell's law. There is one angle that you can come into a new material and go through that material and not have any sort of redirection of that light ray. And that is if you come along the normal line. If a light ray comes in that normal line, then in something like Snell's law, theta is 0. Right? And so theta is 0, sine of 0 is 0. The other side of the equal sign has to be equal to 0 too. So what I'm really kind of thinking through here is, something like this, right? Snell's law. And if theta I equals 0, and that really means that you're coming along the normal line, right? So all angles are measured with respect to the normal line. Along the normal line. Then theta t has to be 0 because you have a sine of 0, which is 0. The other side of the equal sign has to equal 0 too. And the only way to get that is theta t is 0. And so what that really is telling us is something like this. So that's kind of just, us doing a calculation, but having this ray that we can draw, kind of prevents us from having to draw this or do this calculation, I should say. Okay, so if you have a lens like this, and here's really kind of the center point of this lens, and if you've got an object right here, and a light ray comes right towards that center point. Okay, so it hits that front face, and now it's supposed to refract. But the fact of the matter is that it's going to go through that point and just keep going in a straight line. And you go, why does it do that? And that is because the normal line for this material right here, and I'm sure glad that my technology got rid of that. The normal line is right here. And so if I imagine a right angle right there, it's just something just like that. And so, so there's some curvature, and you imagine it like a little straight line in here, and you kind of get in your little right angle there, or something like that. And so you're coming right in on the normal line, and so you get to go through with, no deviation at all. And that's what Snell's law really tells us. Okay, so, when we can't draw ray number 2, we will be drawing ray number 3. Okay, so let's kind of recap here. When light hits a transparent material, it gets redirected. What we're trying to do is find a way to understand that redirection of light so that we can make things that help people. Maybe eyeglasses, binoculars, telescopes, some sort of technology that does some sort of, job for us. And, this is fraught with calculation, and these shorthand little rays to draw kind of prevents us from having to calculate and calculate and calculate and calculate. And so that's what's really kind of happening here. And so there are 2 typical ways that we shape material. We kind of have the converging, lens, which is fat in the center, and then you have the diverging lens, which is kind of skinny in the center. And they do kind of opposite things with the light, right? The converging lens actually gets the light and really brings it to a point, converges it. And then, the diverging lens gets light and then really kind of spreads it apart. And so, they're doing 2 different things, and, different circumstances will require, one or, sometimes both of those types of lenses here. Okay, so that's the idea. Okay, so, I think at this point, what we're going to do is take a look at maybe a sheet or 2 that, you've got in your material. And I would really suggest having a straight edge for this. You really want to do this. And the minute I put a ruler down on my screen, just that very slight touch gets the screen to resize, shrink, do all sorts of funny things. So I'm going to do the best that I can, just kind of freehanding stuff like that. So only the tip of this kind of goofy little pen here is really touching here. But really, I think you should have a straight edge, and these should be very, very beautiful straight line diagrams. That's really what you want to do. So yeah, find a ruler. And then let's take a look, see maybe at this sheet right here. And so you've got a sheet in your package of stuff, available on Canvas. And at the top it says convex lenses. Okay, a convex lens is another name for a converging lens, which is another name for a positive lens. Okay, so these lenses have considerable number of names. And so your eye doctor will sometimes use them very quickly, interchangeably, because to he or she, this is just meat and potato stuff, right? This is just everyday stuff. And they just realize a converging lens is a positive focal length lens, and it's also called a convex lens, as opposed to a concave lens. A diverging lens will be concave. Okay, so what we're going to do is have an object, and so here's the object right there. And so let me see here. So here's the object right here. Okay, and it needs to touch the optic axis, and so I've got the one end of the object touching the optic axis here, and I'm going to draw light rays from the top of the object, the little arrowhead, and see what they do when they hit this transparent material. The transparent material is going to redirect the light rays, and how it redirects them is going to give us an indication of how we might be able to use this lens here. Okay, so that is really the idea. Okay, so I am going to draw ray number 1. Ray number 1 comes from the top of the object and it comes in parallel to the optic axis, hits this transparent material, really refracts at the front face and the back face. But I'm not going to do 2 calculations. I'm just going to redirect that ray right through the focal point and bypass my calculations, because the calculation will tell us that it does exactly that anyway. And so light comes from the top of this object parallel to the optic axis, okay? Hits this material and gets redirected. How? Through the focal point. And do this with a ruler. Do that with a ruler. That right there is ray number 1. Parallel to the optic axis, and it gets redirected through the focal point of the lens. That's what the focal point means. Any rays that are parallel to the optic axis get sent right through that point. Okay. Now, you might have a choice, and that's okay. I'm now going to draw ray number 2. Ray number 2 is going to come from the same exact spot on the object. So I'm really trying to see the spot on the object, how is it getting mapped out on how these rays are getting redirected by the material. So ray number 2 is going to go from the top of the object and it's going to go through that focal point, the one that's on the side of the lens that the object is on. The light's going to hit the lens and then get redirected. When it gets redirected, it will leave the lens parallel to the optic axis, right? So look at the words on ray number 2 again, very, very carefully. And it says that, a ray coming from here and goes through the focal point, hits the lens, and then gets redirected parallel to the optic axis, just like that. Okay. At this point, I am really done. I can draw the 3rd ray, and I think I will. But at this point, I don't really need to go any further in the analysis. I have in front of me what I really need to know. Okay, and that's because ray number 1, the one drawn in red, and ray number 2, the one in green, once they've gone through the lens, they actually hit each other. They intersect. And that intersection point is what I really need here. Okay. But if you were to draw the 3rd ray, the 3rd ray would go right through the center of the lens, right there. So I'm just going to draw a little dot right in the center of the lens, right on the optic axis. And if a light ray came from the top of this object and was hitting right for that point, it hits the material, but this one gets to go through the material with no deviation at all. And so it looks just like that. Okay. And so all 3 points converge on a point behind the lens. All right. So it would not in this case mattered if I had drawn ray 1 and 2, I had that same conversion point. If I drew ray 1 and 3, I would have that same conversion point. If I drew ray 2 and 3, I would have exactly that same point. So as long as you get 2 of these light rays to cross, that point right there is carrying information that is bounced off of the top of the object. Okay, so in other words, the top of the object, when I say the top, I mean this little arrowhead right here. That little arrowhead part of the object is getting mapped to this spot over here where these light rays are converging, because they all came from that spot, right? And they all hit different parts of the lens, because they went from, when light hits, some object, it bounces off in all sorts of directions. Some of those rays hit the lens, but these rays are all converging on that point. And so that's carrying information about the top of the object. So I'm drawing my little arrowhead like that, okay? And now what we do is we describe what the light did, okay? And that description typically has three parts to it. But this thing right here has got a name, and it's called the image. It's what happened to the light once it went through this piece of glass or this piece of plastic that was shaped this way. It formed an image. In other words, light bouncing off that object got redirected in a certain way, and that's the way it would get redirected and make that image right there. Okay, so that image, typically you are asked to fully describe the image. And that means that you really have to supply three pieces of information. Okay, fully describe the image means that you're going to supply three pieces of information. And some of them are very easy to do, and one of them seems a little odd, but I'll try to give you some way to kind of think about this here in a minute. Now notice that if the object was my pencil, I kind of started with it really kind of like upside down, right? And this was the optic axis, and I had my lens over here, and I was looking at light bouncing off the top of this object. But now the light bouncing off here, once it went through, this is my lens, once it went through the lens, this is being mapped up here. And so the image looks like that now, right? So the object had this orientation, but once the light got redirected and the light rays came together, it has that orientation. What we'd say is that the image is upside down from the orientation of the actual object. And so we don't have to write all of that out. We just typically write one word. And that one word would be is that the image, or what we want to do here is we want to describe the image. The image is inverted. That means it is upside down. Okay. That is 1/3 of the description. The next third of the description is the object has a certain size. And so I'm going to come in here and erase a little bit of these lines that I drew here. Okay. And the size of the object is this right here. Okay, that's the size of the object. Eventually, your textbook will call that H for the height, with the little O for object. That's the height of the object. This right here is the height, the little I, height of the image. And to my eye, the image looks a little bit smaller than the object. And so the image, since it's smaller, we would say it's minified. If the image is bigger than the object, then it's magnified. So in this case, it's minified. And I can think of some very, very important places where I might want something like that to happen. This might be, for example, a camera lens. Okay, so imagine, in the old days, 20 years ago, your camera had a piece of film in it. And most of you may have had the opportunity to look at a piece of film, but the actual film is maybe like an inch by an inch, right? So you have a little block of material there, and you open a shutter, and light comes in from those objects, hits this lens, and then it has to land in this little area here. Not much different than what's happening in today's phones and so forth, right? There's a little spot where light comes in, and it lands now not on a piece of film, but it's landing on probably like a CCD chip, most likely. Some phones may have something a little bit different, but most of them have a CCD chip. And that light then lands on something very small. But what you're looking at might be really big, right? You might be taking a picture of a tree. The tree may be 80 feet tall, but you've got to make it land on pixels that are maybe only, like 1 centimeter square or something like that. And that 1 centimeter square may have, you know, a couple thousand pixel array and so forth. So you've got to get that tree and somehow minify that, shrink down all that information so it fits on your piece of film or in your CCD camera, you know, on that little chip. And so, you know, having an image that's getting minified is something that, you know, is of just practical importance, right? You have a 2 meter tall man and you want to take a picture of that person. Well, you gotta, you know, get that image and get them to fit, you know, on that piece of film or on that CCD chip somehow. So you don't want the camera to be life size, right? The camera is something that people carry. So, you know, it's important that we are able to minify objects too. Sometimes we want them to be bigger, maybe like in a telescope or a microscope. Sometimes in a camera, you want them to be smaller. So there's, you know, very important uses here. Okay, so I think the first two descriptors of the image are pretty easy to get along with, right? If the object gets turned upside down, its orientation with respect to the image, then it's inverted. If it's bigger, it's magnified. If it's smaller, it's minified. So those two just, you know, just kind of come out of the word work. In this case, the image here is called real. And this is the one that gives, you know, people the first time seeing this type of description some issues here, because they're thinking that, okay, well, so an image is real or it's what, fake, and it's not, right? This word real doesn't have anything to do with like reality or being real or fake. It's really an awful name to describe what we've got here. But the definition of a real image is that if you were to put a screen, and your screen could be like your hand, it could be a piece of paper, it could be anything, and if you put it right where the image is being formed, you would actually see the object there and it'd be upside down. Right? So if you really have your pencil upside down like this, and then you put a lens here, and the light coming off this goes through the lens, somewhere downstream, if you put your piece of paper up, you will see this object, but it's going to be right side up and it's going to be smaller on your screen. So if you can actually put a screen there and look, you go, oh, I see it on the screen, then it's real. Okay. So it has nothing to do with like reality or anything like that at all. It's just a name that it can actually land on a screen, as opposed to something that does not or cannot land on a screen. And I'll show you what that kind of means in a moment. And so this right here would be, you know, the screens. That's the screen's location for a clear image. If you put the paper somewhere else, it'll be out of focus. It won't look that good to you. You'll kind of be able to tell that maybe you're looking at a pen, but it's going to look fuzzy to you. And so you just kind of keep moving the screen around a little bit. And so, you know, a lot of times with like a projector, you know, you have a lens up front and you start turning something and it starts moving the lens a little bit. And so that's the same as moving the screen, right? So you're moving something back and forth until you kind of find that right spot, because the geometry of straight lines, which light travels in, tells you that's where the light rays are intersecting. That's where the image is being formed. That's where you put the screen. And so if this lens is in front of your eye, and that's your eye lens, and it's forming an image at that location, if that's not the back of your eye, you need glasses. Right? We need to redirect the light so that it forms the image on the back of your eye, which is the screen. And so if it's not landing on the retina, yep, you're going to need some sort of, you know, accommodations somehow, you know. And so maybe that was a poor word, because accommodation is actually a word that the eye doctors will use, which means that the lens in your eye is, as you age, gets more crystalline and it gets harder. And so it really can't vary its shape. And so the lens in the camera is a piece of glass and it has a focal length. The lens in your eye is something that could be moved a little bit. So it has a variable focal length. And so the older you get, you start losing the ability to have that, that variation because the lens just gets kind of too hard. And so now the cilia muscles can't really stretch it or squeeze it down and change its shape, which changes its focal length. And so then, you know, you've got this thing that you're losing accommodation, the ability to have a variable focal length here. Okay, but a full description is going to be inverted, or if it doesn't get turned upside down, you just say not inverted, or sometimes you see the word upright, so it did not get turned upside down. Minified or magnified, real, and if it's not real, then the word that we use is called virtual. And I'll show you what a virtual image happens to be. Now notice, you know, up above at the top of the sheet here, it's exactly the same lens as what we were just using, has exactly the same focal point, right? So, you know, F's look like they're in the same spot. The focal points are, you know, they look like they just line up nicely. The lens has exactly the same shape. It has the same location. And all we did was move the object from outside the focal point to inside the focal point. And so in this case, we're going to have a different description, right? So it's going to depend on where the object is and how the light rays bounce off it, how they get redirected. And that will give us then the description that we need. So in this case, I'm going to draw ray number 1. It's going to bounce off that object, but it's going to be parallel to the optic axis, hit the lens, get redirected, and it's going to go through the focal point. So I really stress that, you know, these should be very, very tightly drawn diagrams, really with a ruler here. But every time I try to use one on this little touch screen, it just messes up here. So I'm going to draw ray number 1. Comes in parallel, hits the lens, and then goes through that focal point just like that. Okay. So in the description of the rays, that was what we called ray number 1. Parallel to the optic axis, hits the lens, and then gets redirected through the focal point of the lens. That's what ray number 1 looks like. Okay. Now notice here that we cannot draw ray number 2. You can't have a light ray come off the top of that object. When I say the top, I mean the little arrowhead, go through the focal point and hit the lens, right? So you can't do that. So we cannot draw ray number 1. So I'm going to draw ray number 3. And ray number 3 means I'm going to put a little dot right at the center here. And light is going to come right through here, and it goes through undeviated. So it kind of goes through just like that. And so this is ray number 3. Because I don't think we can draw ray number 2 here. Okay. Those light rays, once they've passed through the lens, are getting further and further apart, right? So light rays go in straight lines. They're never going to come back together here, right? You know, this cannot be a real image. A real image, the light rays actually converge to a point once they've gone through the lens, like we have in, you know, part B here. Okay, so what does that mean? Once again, your eye and your brain, because of all the experience that you have, tells you that light rays are getting to your eye by going in straight lines. Okay, so if your eye is out here, so this is your eyeball, here's your eyelashes, right? Okay, and ray 1 and ray 3 are hitting your eye. Your brain is saying those 2 rays came in a straight line, and forget that the lenses are redirecting them, right? Your brain doesn't care. It just says, no, they came in a straight line. And so that's what you do. You say, oh, okay, ray number 1 came in a straight line. It came from this straight line. So I'm going to just backtrack this all the way, you know, kind of down in here someplace. And ray number 3 is coming to my brain in a straight line as well. And so that straight line would be, you know, like right here, something like that. And I'm going to hit this spot right here. And that's where the two rays that are kind of back mapped, that they're hitting my eye from these diverging rays. And your brain says, oh, they're really coming to you in a straight line. So if I kind of back those lines down, it looks like they're coming to me from this point right here. And that point is carrying information about the top of the object. So to your brain, with these rays coming in like this, it's seeing that this little object like this is coming from something that looks bigger now. Okay, and so now if we describe this image, okay, this image is upright because the orientation has not changed. So you've got a little object whose orientation is like this, and now you've got an image who is bigger than that, but the orientation is still the same. So it's upright, it's magnified, and this is what we call virtual. This is a virtual image. And that's because over here, there is no real image. Why is there no real image? Because the light rays did not come together at a point somewhere behind the lens. Okay, they're getting further apart behind the lens. And so if your eye is behind that lens and it sees these rays coming from the same object, but they're coming at you from these vastly different angles, your brain just kind of backtracks as well. That object is really over here because the light rays are really not coming in, hitting a piece of plastic and being redirected in some sort of profound manner like they are here. It really came to me, you know, from this object that is out further from the lens, and it's not upside down, and it's bigger. Ah, that to me sounds like a good use for reading glasses. Reading glasses better not turn the stuff upside down, right? That's no good. Reading glasses typically make things bigger. Oh, I like that. And reading glasses create virtual images, right? So your glasses are virtual image makers. So you put something out in front of the lens, light bounces off it, hits this, and then it gets redirected, comes to your eye, and your brain sees these rays, the light coming from these rays is coming at these funny angles, and your brain is saying, oh, it's really coming from an object that's out here, but the object's not that big, it's really that big. And so now the print on the paper is larger to the interpretation to your brain, right? And so, and it's not upside down. And so that would be something like reading glasses right there. Kind of interesting that your lens in your eye, right, your natural lens, behaves just like picture B right there. Light hits it and it gets turned upside down, and it forms an image on the retina, a real image on the retina. And then your brain has learned in the first few months of your life that even though the lens system is inverting the light rays, your brain interprets things, you know, the other way. You know, that is right side up. But that's something that your brain is coping with, you know, in those first, you know, 6 months of life or whatever. You know, as your eyes are starting to see things and is trying to make sense of the world. So, you know, the image on your retina may be upside down, but your brain is able to cope with that, right? And so, you know, this is something that, I don't know, those people in psychology and stuff do. So, you know, they've done these experiments where they get a lens, like glasses, and put them out in front of somebody's eyes that will invert the image before it hits the eye, which then inverts that image. And so then the image on your retina is actually upright, which is completely different than all of your life experiences. And it takes people about 2 weeks or so, and their brain is able to reinterpret that upside down image, and they kind of function kind of normally. You know, so I think, you know, once they've done those experiments, you know, the brain is able to kind of cope with that. The problem is once you take those glasses back off the people, then the brain didn't know what to do, because it sort of lived, kind of in both worlds, and it says, no, I don't know what to do now, right? So then the psychologists have messed you all up or something like that. So anyway, so that is a full description of the image in each case. The image in the letter A, upright. Yep, it did not get turned upside down. It's bigger than the object, it's magnified, and virtual, which means that we had to backtrack the light rays. So you had to backtrack these light rays back in here to this intersection spot. And your brain is telling you that's where the top of the object really is located, because it wants straight line paths for light. And so if you look at your paths here, everything here is being just straight lines, and that's all that's really happening here. So very, very nice geometries here to really kind of deal with. Now, on this one, what we're going to do is put the object right on the focal point. So you notice up here, we have an example where the object is outside the focal distance. That's letter B. Letter A, you have an object inside the focal point. And here we put an object right on the focal point. Okay, and really try to draw this the best you can with a nice straight edge, and I think that's going to make life kind of nice. So I'm going to draw ray 1 here. And it's going to come in, hit here, and it's going to hit that focal point. And I'll try to get that going in a nice straight line. So there's ray 1. I can't really draw ray number 2. I can't have information coming from the top of this going through the focal point, which is kind of at the foot of the object, and go through the lens. So it really can't do that. So I need to really kind of maybe go to like ray number 3, which means I have to go right through that middle of that lens there. And it hits, and if I'm careful, be very careful drawing this. If you draw these very carefully, what you'll notice is that these two rays right here are parallel to each other, which means they don't meet once they've passed through the lens, which means that there is no real image. So you go, aha, I just learned something. That means if, I've imagined my eyeball being back here, and these rays are hitting your eye, your brain is saying, well, light just travels in straight lines. So I get those straight lines that the light came in on, and I kind of backtrack those. And your brain is telling you, well, that's exactly what light does in all circumstances of life. And when I backtrack those, if I'm careful, what I see is that they're parallel on this side too. Okay, and so the light rays, once they've gone through the lens, are parallel. When I backtrack them very carefully, they should be parallel. So that means there's no virtual image either, because you need the light rays to come together. So here there is no virtual image either. Okay, so if there's no virtual image, that means that there's no image being formed at all. So if you put an object right on the focal point of a lens, you create no image whatsoever. Okay, and so this might be, if somebody hands you a lens and says, measure the focal distance of this lens. Well, what you can do, take a look at your pictures here. Right? You can get an object that is far from the lens, outside the focal point, right? And you form a real image. And so that might be as simple as taking glasses off, looking at objects that are lit up, maybe outside, trees that are a block away or something like that. They hit the lens, then you just use the wall for your screen, and you just kind of, start moving the glasses around and so forth, and see if you get a real image, and you do. And then you start moving the glass closer and closer to the objects, like you've got in that first one, and eventually your real images disappear, and then you have just virtual images, which you have to have the glasses on to see, because they don't actually hit the screen. And so where you lose the real images and where you start forming the virtual images is, that flip spot is really right at the focal point. So if the object is outside the focal point, we get real images. If it's a converging positive convex lens. If it's inside the focal point, like that first example, then we get virtual images. And if it's right on the focal point, we get no image. So do you memorize that? Yeah, why not? That's not that hard to memorize. Far from the lens, real images. Close to the lens, virtual images, just like reading glasses, right? If you're actually right on the focal spot, yeah, you form no image there at all. Okay, so those are the full descriptions that we need for these images here. So let's take a look here. Let's go to the second page here. Okay, and the second page has two lenses, and so this might be something like a telescope. They've got typically two lenses at a minimum. You know, this could be a microscope. This could actually be a camera lens or something like that too. And so what we're supposed to do is determine the location of the image. And what we're going to do, we're going to describe the image. And the image is once the light has gone through both lenses. And doing something like this is not very difficult, but there's this kind of little rule of thumb that we need to really kind of remember here. And that is something like this. That is the image formed by the first lens acts as the object for the second lens. I'll have to do something like that because I'm running out of room there. All right, so so I'm going to have light bounce off the object, go through the lens, and form an image. And in this case, I already know that I form a real image because the object is outside lens number one's focal point. It's going to form a real image. That image essentially is like the object for lens number two. Lens number two essentially sees an object right there with light bouncing off it, and it will act just like the object for lens number two. And so, you know, your job here is to produce using the rays to draw. I'm going to draw ray number one. There's ray number one right there. Comes in parallel, and it gets sent right through that focal point, just like that. And get that going as straight as you can with a straight edge. So there is ray number one. And then I'm going to draw ray number two, which I can. Information from the top of the object goes through that focal point, hits the lens, and then comes off parallel. And I've got a spot right there where there's an intersection. And so that is the image. That is the image formed by lens number one, which means that that is the object for lens number two. Okay, so what you could do is start erasing stuff, but you know, I think it's better not to, even though it might look a little cluttered. Essentially, you've got an object sitting right there in that location. And so if this is my object right here, and I have light coming off of this, and it comes off parallel to the optic axis, and it hits this lens, that light ray has to get deviated right through that second focal point. So that's just ray number one coming from this object here, which is now acting like, you know, that's acting like the object for the second lens. And then, you know, you need to draw a second ray to see if it, you know, meets up with ray number one that we just drew. And so since we're outside the focal point, you can draw ray number two, right? Information from the top of the object can go through the focal point, hits the lens, and gets redirected. But that ray will get redirected parallel to the optic axis. And so there is the final image formed by the lens system, by both of the lenses here. And so if you were to describe this, notice the object started kind of, going this way, and then the final image is going up that way. And so you would say that it's, upright or not inverted. In my case, I wasn't really using a ruler and so forth, but maybe it looks a little bigger. So maybe this is a little bit magnified here, but that might be debatable. And since light rays really kind of came together here, this is a real image. So you can put a screen right there, since light rays are actually intersecting at that spot once they come through the lens. You would put a screen there and you would see the object, and it would be a little bit bigger, it would be a little bit upright, and that's exactly really kind of what you want there. Okay, so when you have a series of two lenses, you just do each one separately, and you form an image from the first lens. That image acts as the object for the second lens, and you just kind of do your ray diagram again, and then you find your final image, and then you can describe that here. And so here you've got a final real image that's upright and so forth. And so yeah, this might be wouldn't be a very good camera system if it's really making things bigger, but this could be like a terrestrial telescope. Terrestrial means that you're looking at things on Earth, like if you're looking at birds or something, you're looking at the opposing army or something like that. Some telescopes turn the objects into an image that's upside down. That's called an astronomical telescope, because if you're looking at a star and it gets turned upside down, you can't tell that anyway, right? It's just a point of light. Or if you're looking at the moon and it's upside down, you really don't know that either. But if you're looking at a tree and you're looking at a bird in the tree and the whole thing is upside down, that, okay, now is disorienting, and that's not really what you want here. But so this might be like a terrestrial telescope. It's making things bigger and stuff like that, keeping them upright here. So that'd be just kind of an example of what you can use a two-lens system like this here for. Okay. This idea of magnification down here, your textbook uses some very good notation here, and I'll kind of show you that notation here in a moment. This picture right here that we're going to end up drawing here with our ray diagrams is going to be very important. So you really want to do this as neatly as you can. Use a ruler, because this is going to be the start of our mathematics, I think. And that's why I really kind of put this here. So in this case, the object is a pencil instead of just a little arrow, but it's kind of the same idea. And what I'm going to do is form an image. And in fact, it looks like the image is already formed. So I'm just going to draw my three principal rays. And then I'm going to come back to this image and start using it, and using just simple geometry that we all know and love, and come up with some equations, so that maybe, if we want more precision on something like, well, how much bigger is the image than the object? Then we could have a number. Exactly where is the image formed? Exactly where do I put the screen to get a nice, clear, sharp view? Well, then I kind of want a number. Okay, and so eventually we're going to want some numbers here. But so, what you should do here is draw, I think, all three of your principal rays. Draw all three of them as carefully as you can with a straight edge, and see exactly what you get. But the image is already there, so that means that your rays have got to be done here with some precision. So, for example, if you were to have light bouncing off the top of the object and it passes through the lens, those rays could be coming in all sorts of different orientations. But one orientation is that the light could come in parallel, hit this lens, and that has to go through the focal point, and then it just keeps going in a straight line. So there's ray number one. Do that with a ruler. Ray number two would be kind of the inverse of that, going through this focal point, hitting the lens and then coming off that parallel, right? So there's ray number 2. And then ray number 3, you've got to put that little dot right in the center of the lens. And light comes off the top of the object and it comes in essentially right on the normal line of that lens, which means through Snell's law, it goes through undeviated. So it's got to go right through that point here. So that's where the top of the object is getting mapped. So the image then is inverted here. And if you are clever, you've got just about everything you need kind of in front of you. I might, change the picture here maybe a little bit, but I don't think we'll need a lot. But in essence, what you want is, if someone says, I have this kind of lens, what that means is, here is the focal length. That's how you describe the lens. And then that focal length is going to have a positive sign or a negative sign. In this case, looking at that lens, that's a converging or a convex lens. This is going to have a positive focal length. So if someone says, okay, the focal length of that lens is plus 10 inches. Okay, if I know that, and I tell you where the object is located relative to the lens, so that's just a distance on a ruler, I want mathematics that tells me exactly where the image is formed. Exactly where do I put a screen? And that's the mathematics that we want. That's the specificity that we want. That if I tell you what kind of lens we have, I tell you where the object is, you can tell me exactly where the image is. Now, we could do exactly what we just did right here, and we could get fairly good precision if we did this drawing, one with rulers and number 2 on graph paper, where it was really scaled, where we had the focal lengths at exactly the right scaling positions. We put the object at the right position, and then we can draw these rays, see where the image is formed, and then just count boxes, and that would be, equivalent to some distance here. What we want to kind of do is something like when in chapter 3, when you're adding vectors, and you're adding vectors graphically, and you put them head to tail. When you put them, head to tail, you can kind of have an idea of the length and the direction. But to really get the precision, you really want to do the mathematics here. And so that's what we really want here, right? Your eye doctor doesn't want to be kind of guessing what the answer is going to be, right? You really kind of want this precision here. So this last picture here, I think, is going to help us get to that precision that we really kind of need here. And this right here, from here to the lens, will be called DO, the distance that the object is from the lens. So given that, given the focal length, you should be able to predict, really this distance. And that's called DI, which is the distance that the image gets formed. How far from the lens? That's where the little eye comes from. Now, this whole thing up here is predicated on this idea of magnification, okay? And so magnification will be really just what you kind of think it is. This is the height of the object. So let's see here. My pen no longer wants to write. So we're going to put that as an H with a little O, height of the object, and we'll have a height of the image. But this is where we're stopping really in this lecture. And so I will, once I get the pen working here again, we'll come back to this, and we're going to develop mathematics right from this picture here. So I may clean up the picture a little bit, but really kind of keep this in mind. And I think you can do this too, because if you start looking here, you've got a whole bunch of triangles to play with. And there's probably a bunch of congruent angles in here and different things like that. And so there's probably a bunch of stuff that you can relate to each other, so that if someone tells you DO, and they tell you F, the focal length, you should be able to predict DI. So if you can come up with that, that would be very, very good. And it's not that difficult to do, but you have to look at probably the first, couple correct triangles in here, and it all comes out very fast. Otherwise, you're just kind of jumping around from triangle to triangle. It might take you a while. So give this, some thought. The next lecture, we'll be starting with this picture right here, developing the mathematics and then using the mathematics to make predictions with precision. So we'll refine this approach here, but this approach, really helps to do these types of problems really fast, especially you can just kind of imagine what a couple rays would do where they meet up, and you can get a full description of the image very quickly. Real, virtual, bigger, smaller, magnified, minified, or upside down or not upside down. And so that's really kind of what you want to be able to do. Okay, so I hope this helps with the sections on ray tracing for lenses. So in chapter 23, it has many topics. And so I really started with refraction in Snell's law and critical angles. That was the first lecture in chapter 23. Now ray tracing with light going through a material, refraction. And then we're going to, instead of using Snell's law here 2 times for each ray, since the rays behave in these lines that we've drawn, we're just going to use the straight line geometry to bypass the law of refraction and not have to do it twice for each ray. We just have to use one equation. And so that's going to be a great time saver. Otherwise, we'd have 6 maybe calculations to do here for each ray from the front face and the back face to see exactly what it's going to do. So that's something that we don't really want to encounter. And so there's ways around it, which is kind of nice. And so, the next lecture then will be on still lenses, and then we're going to do the same thing for spherical mirrors. What do light rays do when they hit mirrors? Well, they reflect, and they reflect in straight lines. And then we're going to curve the mirror so that we have something interesting to talk about. And then we'll see exactly what takes place there. And then we can start making, nice, large astronomical telescopes and things like that, because mirrors are much easier to make than something like a lens would be. So I will see you soon. And so keep working through chapter 23. Right? It's going to take us, at least another week to kind of get through that and get through all the topics. So there's just a lot of good stuff, and then we'll just kind of take them topic by topic by topic. So I will see you soon, and just kind of hang in there and keep working through chapter 23.